Hello and welcome back. In the previous video, we discussed the lens equation, which allows us to find the location and height of an image formed by a lens. In this video, we'll discuss the images that are formed by mirrors. Now, it turns out that there are two different types of mirrors which are capable of producing images. Concave mirrors, like this mirror shown on the left, and convex mirrors, like the mirror shown on the right. And it's very important that you know the difference between a concave mirror and a convex mirror, because in many of the problems that you'll see in the homework, as well as the problems that will appear on the AP exam, you'll be told that a mirror is either concave or convex, and the difference between these two is very much like the difference between a converging lens and a diverging lens, so this will affect how you calculate the position of the image that's formed. In fact, if we take a look at the concave mirror that I have shown on the left, we can see that the parallel rays are deflected towards each other so that the rays converge. However, when parallel rays strike the surface of a convex mirror, these rays are deflected away from each other, so that the rays diverge away from each other. And one little trick that I see a lot of students use to remember the difference between a concave mirror and a convex mirror is that a concave mirror has the word cave inside it. And if we look at the shape of this mirror, we can see that it sort of is shaped like a cave. It sort of encloses this area in front of the mirror in the same way that a cave would. Now, one useful way to think about what happens to light when it strikes the surface of a curved mirror, a concave mirror or a convex mirror, is that it behaves almost exactly like placing a lens directly in front of a flat mirror. So let me just sort of draw a little picture to sort of illustrate this idea. So if I draw a lens that's placed directly in front of a flat mirror like this, and now we consider what happens to the rays as they pass through this. Well, if we just had the lens there, then the rays would come in and then they would focus down like this. However, because the mirror is behind it, these reflected rays get reflected over to the other side. So instead what happens is these rays kind of go like this. So in fact we can see if we look at these rays, this is basically identical to the types of rays that you get when light reflects off of a concave mirror. So if I have a concave mirror like this, and I look at the light rays that are reflected off of this, they also are reflected back towards each other so that they converge. So this is a really useful way to just sort of think about what's going on when the light hits a concave or a convex mirror. It's basically like the light is passing through a lens and then is immediately reflected back. Now, it turns out that it is really difficult to actually create a curved mirror which is capable of producing a perfect image. And the reason for this is that the shape of that surface that you would need for your mirror is a parabolic shape, and it's just very difficult to grind any type of surface into a perfect parabolic shape. However, it turns out that a spherical surface behaves almost exactly like a parabolic surface, as long as the dimensions of that mirror are much smaller than the radius of the sphere that mirror is taken from. So what exactly do I mean by that? Well, suppose we have this very large spherical shell. So let me just sort of draw a little shell over here. The idea is that I could create a mirror, or something that behaves very much like a perfect mirror, if I just took a little chunk of this spherical surface. Okay, so what I've taken here is just a little piece of the sphere. And now if we look at this little piece of mirror, this isn't like very curved. This is only very slightly curved because I've just taken out a very small piece of this spherical surface. And as long as the height and width of this little piece of surface that I've taken is much smaller than the radius of the sphere that I've taken this piece from, then when I coat this with some kind of reflective surface, this will behave very much like a perfect mirror surface, so that the light that's scattered off an object in front of this mirror will almost perfectly form an image. So how do we show that the light reflected from a spherical surface does in fact form an image? Well, recall that the basic property we use to show that lenses form images was that parallel rays all cross at the same point after passing through a lens. And in particular, we spent a lot of time focusing on rays that were parallel to the principal axis. Recall that rays that are traveling parallel to the principal axis will all cross at some point on the principal axis, and we call that point the focal point of the lens. And the distance between the lens and the focal point was called the focal length. So what I would like to do is I would like to show that any ray that is traveling parallel to the principal axis, when it strikes a spherical mirror, this ray will be reflected back and it will cross the principal axis at the same point no matter where it strikes this mirror. So over here on the right, I have a ray diagram showing a ray traveling parallel to the principal axis and then striking a spherical surface. And I have 4 points labeled on this picture over here on the right. This point C is very important. This is the center of this spherical surface. So I just have a small segment of a very large spherical surface, and this C here is the center of that sphere. The point P is where the ray traveling parallel to the principal axis strikes the mirror. X is where that reflected ray crosses the principal axis, and S is where the principal axis meets the mirror. So basically what I would like to do is show that this distance right here, which I'm going to call XS, doesn't depend on the point where the ray meets this mirror, this point P right here. And basically the way that we're going to do this is by relating two triangles in this ray diagram over here on the right. Specifically, we're going to look at the triangle formed by the center of the sphere, this point P, and this point S right here. And then another triangle formed by the ray, this point P, and the point S as well. So we have these two triangles here, and what I'd like to do is find some way to relate these two triangles so that I can calculate this distance XS. And the first thing that we need to do is we need to figure out what this angle is going to be for this reflected beam. Well, remember that the law of reflection says that the angle of reflection is equal to the angle of incidence. And remember that we measure both the incident angle and the reflected angle with respect to the direction that's perpendicular to the surface. So here's my surface right here, and the direction that's perpendicular to the surface is given by a line drawn from the center of the sphere out to the surface of the sphere, right? If you think about, let me just draw a little picture here. If you think about a circle, if you draw a line from the center of the circle out to the edge of the circle, that's always going to cross this circle at a right angle. So here's the center of our sphere. If we draw a line from the center of our sphere to the surface of our sphere, this is going to form a right angle with the surface. So this means that we should measure our incident angle between this dotted line here and our incident ray. So this is our incoming angle, or our incident angle. And the law of reflection says that the reflected angle is equal to the incident angle, so this angle is equal to this angle here. So these are the same. So now hopefully you can see this line here is parallel to the principal axis. So we have these interior angles, these opposite interior angles. So that means that this angle here is equal to this angle here. Similarly, we can see that this angle here, so this 2 theta angle here, is going to be equal to this 2 theta angle here in this triangle, this yellow triangle. And now the big trick to showing how we calculate this length, XS, is realizing that if these rays are all very, very close to the principal axis, that means that this height right here, the height of this mirror, is much, much smaller than the radius of the sphere that the mirror comes from. Then what we can do is we can use this approximation, this small angle approximation, right? So if we look at this triangle right here, we can say that this length, PS, this length is approximately equal to the arc length that's traced out by this angle theta, right? So this length of this triangle, that's approximately equal to this arc length formed if we just kind of rotated through this arc theta. And of course that arc length is equal to, the length of this arc is equal to the radius of the circle times this angle. So this length right here, PS, is approximately equal to theta, when theta is measured in radians, times this length, which is equal to the radius of our sphere. So this length right here is approximately equal to theta times r. Now if we look at this triangle right here, we can do the same type of a thing. So I can say that this length right here is going to be equal to, so this theta times r, this has to be approximately equal to 2 theta times this distance, xs. So now I can solve for this length, xs, and if I do that, I can see that this is going to be equal to r divided by 2. And this distance right here, this is the distance between the mirror and the point where the reflected ray crosses the principal axis. So this distance, xs, this is equal to my focal length for this mirror. And now the big point that I want to point out about this is that this result that I just came up with didn't depend at all on the point where this ray hit the mirror. So it doesn't matter, for example, if the ray, suppose it were up here, it would still cross at the same point down here. Okay? And in fact, all of the arguments that we just used through this whole derivation, all of those would still hold, as long as this mirror, this distance between the principal axis and our incident ray, as long as that distance right here is much, much smaller than the radius. That way we can assume that these angles are all small, and we can assume then that these arc lengths are approximately equal to these lengths in these triangles down here. And this is an extremely important formula, this relationship between the focal length and the radius of a spherical mirror. And the reason this is so important is because in many of the problems that you'll see on the homework and on the test that involve spherical mirrors, you'll be given the radius of the spherical mirror instead of the focal length. So you have to know that the focal length is equal to the radius divided by 2. Now in the previous slide we went through this calculation looking at a concave mirror. And it turns out that for a concave mirror, we say that the focal length is greater than 0. However, for a convex mirror, remember that's a mirror that causes the beams to diverge after they reflect off of the mirror, this will have a negative focal length. So for a convex mirror, the focal length is equal to minus the radius of curvature divided by 2. So now that we've established that the light reflected from a spherical surface does in fact form an image, let's discuss how we draw a ray diagram for the light that's reflected from a spherical mirror. And basically, this is just like drawing a ray diagram for a lens, except when the light strikes the mirror, it's going to be reflected back, so we wind up using the same focal point for all three rays. So the first ray is that any ray traveling parallel to the principal axis will be reflected so that it passes through the focal point of the mirror. So if I draw a ray that's parallel to the principal axis, again I'm going to try to use a ruler to draw this as best as I can. This is going to be reflected so that it passes through this focal point. The second ray is that any ray that passes through the focal point on its way to the mirror will be reflected so that it leaves parallel to the principal axis. So if we draw this ray so that it passes through this focal point, it's going to be reflected parallel to the principal axis, so it's going to look like this. And then the last ray is a little bit different than it is for a lens. So remember, for a lens we said that a ray that passed through the center of the lens just kept moving straight. Well, for a mirror it's a little bit different. A ray that passes through the center of this spherical cavity, when it hits the surface of the mirror, it'll be reflected right back on itself. So this ray that's passing through the center of the mirror will be reflected back on itself. So it's going to travel like this, and then it's going to hit the mirror, and then travel back in the opposite direction. And if we look at these three reflected rays, we can see that they all more or less intersect the same point right here. So we wind up with this upside down image. It kind of looks like this. Now the next thing I want to look at are the ray diagrams drawn for a convex mirror. And again, this is just like the trick that we used for drawing the ray diagrams for a diverging lens, is that we just wind up using the focal point on the opposite side. So here we're going to use the focal point behind the mirror instead of the focal point in front of the mirror. But besides that, everything's going to be the same. So the first one is that a ray that is parallel to the principal axis is going to reflect off this, and if we extrapolate that point back, we'll see that it crosses the principal axis at this focal point here that is behind the mirror. So again, let me try to draw this. So we have a ray that's parallel to the principal axis, and when it strikes this, it's going to leave so that if we extrapolate this beam backwards, it would pass through this focal point. So that's our reflected beam right there. Now the second one is again the same kind of thing. If we directed a beam towards the focal point behind the mirror, it's going to reflect off of this mirror parallel to the principal axis. So let me kind of draw another picture here, another ray. So I'm going to draw this ray and see this ray is going to be sort of directed at this point, and it'll be reflected parallel to this principal axis. And again, I'm going to go ahead and extrapolate this reflected beam back so we can see these two reflected beams are intersecting at this point. And the last one's basically the same as the last ray for the concave mirror. Any ray that is directed towards the center of this mirror will be reflected right back on itself. So if I try to draw a ray that passes through the center of this mirror, again, I'm going to use a ruler to try to do the best I can. So this ray right here is just going to be reflected right back on itself. Actually, it should be, of course, dotted on the one side. Let me try to do that again. Because the ray doesn't actually pass into the mirror. And again, if we look at the beams that are extrapolated backwards into the mirror, we can see that they all intersect at the same point. So we have this image that forms over here. And it turns out that because we've defined the focal length of a spherical mirror in basically the exact same way that we defined the focal length for a lens, it turns out that the images formed by a spherical mirror obey the exact same lens equation. So you don't have any other equations that you have to remember. It's still 1 over dO plus 1 over dI is equal to 1 over the focal length, where dO is the distance between the object and the mirror, dI is the distance between the image and the mirror, HO is the height of the object, and HI is the height of the image. And of course, we could derive all of this again by going back to the ray diagrams and looking at similar triangles. However, I don't want to go through that whole derivation again. Now, because the image is formed by the reflected light, it turns out that the sign convention that we use to describe the location of the image for a mirror is a little bit different than the sign convention that we use for a lens. And the basic rule is that we say that dI is negative whenever the image forms behind the mirror, and dI is positive whenever the image forms in front of the mirror. And a useful trick that you can use to remember the sign convention for dI that works for both lenses and mirrors is that dI is positive whenever the rays actually intersect at a point and form a real image, and dI is negative whenever the rays don't actually intersect at the point, so you have a virtual image. So for example here, we say that dI is positive when the image forms in front of the mirror. So that means that those reflected rays are actually going to cross at some point in front of the mirror and form the image. Likewise, if we think about lenses, dI is positive when the image is on the opposite side of the lens as the object. Again, dI is going to be positive when those rays are actually intersecting at some point to form an image. Now, one last thing that I should show before we move on to any examples is that it turns out there's actually a very easy way that you can remember the focal length of a spherical mirror using this lens equation down here. And let me just kind of show this very simple idea. So if you consider an object that is placed at the center of a spherical mirror, and we consider the rays that are scattered off of this object, well, the ray diagram is going to be really easy because any ray that's scattered off an object that's at the center of a spherical mirror is just going to be reflected right back onto itself. So the ray diagram just looks like this. And so obviously we can see that the image forms right on top of the object. So the position of my object is equal to the position of the image, and both of these things are a distance r away from the mirror. Now if we plug this into the lens equation, so we have 1 over dI plus 1 over dO is equal to 1 over the focal length, So here we have the distance of the image is r, the distance of the object is r, so we have 1 over r plus 1 over r is equal to 1 over the focal length. And of course 1 over r plus 1 over r is 2 over r. So looking at this, we see that the focal length is going to be equal to the radius of curvature divided by 2. So this is just another way to remember the formula for the radius of curvature for a spherical mirror. Now of course, this doesn't actually prove that a spherical mirror will create an image. However, this is nonetheless a really, really easy way to remember that formula. So let's take a look at a couple of examples. The first example says, an image forms 22 centimeters behind a convex mirror which has a radius of curvature of 68 centimeters. The question asks us to find the position of the object, the magnification of the image, whether the image is upright or inverted, and whether the image is larger or smaller than the object. So the basic trick to solving these problems is just figuring out the sign for the object and the focal length. Once you have that, you're just going to plug these things into the lens equation, and then it's pretty easy to solve it from there. So here we're told that the image forms behind the mirror. So this means that DI is equal to negative 22 centimeters. Remember, that was the sign convention that we established for the position of the image, is that if the image is behind the mirror, then DI is going to be negative. We're also told that the mirror is a convex mirror. That means that my focal length is going to be minus the radius of curvature divided by 2. Remember, the focal length for a convex mirror is always negative. So here we see that our focal length is going to be equal to negative 34 centimeters. DI is negative 22 centimeters, and we have the lens equation which says that 1 over DO plus 1 over DI is equal to 1 over the focal length. So I'm asked to find the position of the object, so I see that 1 over DO is equal to 1 over the focal length minus 1 over DI. And I always like to establish a common denominator, so this is going to be equal to DI minus the focal length divided by DI times the focal length. And I do this because now this is very easy to flip this fraction. So if I solve for DO, I see that DO is going to be equal to DI times the focal length divided by DI minus the focal length. And if I plug these numbers into a calculator, I can see that the object is located 62.3 centimeters in front of the mirror. Now the next part of the question asks us to find the magnification. Remember, the magnification is equal to minus DI divided by DO. It's the same equation that we use for lenses. So here we just have to be careful about our signs. DI is negative 22 centimeters, so we have minus negative 22 centimeters in the numerator. The object is 62.3 centimeters in front of the mirror. And if we plug this into a calculator, we can see that the magnification is equal to 0.353. Now the next part of the question asks us to determine whether the image is upright or upside down. Because the magnification is positive, we see that the image is upright. And because the absolute value of my magnification is less than 1, we see that the image is going to be smaller than the object. So the second example says, an object is placed 1/4 of a radius in front of a spherical concave mirror. The question asks us to find the location and magnification of the image and whether the image is real or virtual. Now remember that for a concave mirror, the focal length is going to be equal to r divided by 2. So concave mirrors, remember, they act just like a converging lens, so they have a positive focal length. So here we're told that the object is 1/4 of a radius in front of the mirror, the focal length is equal to 1/2 of the radius, and we're asked to find the position of the image. So we can do this by using the lens equation, so we have 1 over DI plus 1 over DO is equal to 1 over the focal length. So I see that 1 over DI is going to be equal to 1 over the focal length minus 1 over the position of the object. And in this case, because I've been given the position of the object in terms of the radius, it doesn't really make sense to find a common denominator. So if I just plug my values into this, this will simplify right away. So 1 over the focal length, well, the focal length is r divided by 2, so 1 over that is 2 divided by r. Similarly, The position of the object is r divided by 4, so 1 over that is 4 divided by r. So this difference is going to be minus 2 divided by r. So the position of the image is equal to minus r halves. And again, remember this minus sign here for the image indicates that the image forms behind the mirror. So if we go back and look at the other parts of the question asks us to find the magnification. Remember, the magnification is equal to minus di divided by do. So here we have minus a negative r halves divided by do, which was equal to r divided by 4. So here the r's cancel, the negative signs cancel, and we can see that this is equal to 4 halves, or 2. So the image is going to be twice as large as the object, and it's going to be upright. The last part of the question asks us to determine whether the image is real or virtual. Well, again, because di is negative, this tells us that the image forms behind the mirror. And whenever the image forms behind the mirror, the image is going to be virtual, because the rays don't actually travel behind the mirror, so they don't actually cross at that point where the image forms. So I think I'm going to end the discussion on mirrors there, and in the next lecture I'm going to talk about how we handle systems involving more than one lens or more than one mirror.